The Fermi Paradox has finally been solved, and it shouldn't exist like this, because the answer suggests that the silence of the stars is not a mystery of distance, but a mathematical certainty. And that changes everything we thought we knew about the night sky. Because when you look up on a clear night, far from the glow of cities, you see something that should not make sense. You see roughly 4,000 stars with the naked eye. But what you are really seeing is a fraction of what is actually out there. Our galaxy alone holds somewhere between 100 billion and 400 billion stars, and each one of those stars is a sun. Many of them are older than ours. Many of them are bigger. And as we have only recently discovered, most of them have planets. That last part is important, because for most of human history we did not know that. We looked up and saw points of light and wondered if anything else was out there, but we had no way to answer the question. It was pure speculation. Beautiful speculation, but speculation all the same. Then the Kepler Space Telescope changed everything. Between 2009 and 2018, Kepler stared at a single patch of sky and watched for the faintest flickers in starlight, a tiny, repeated dimming that would tell us a planet had passed in front of its star. And what Kepler found was staggering. Not just a handful of planets, not a few dozen, thousands. Kepler confirmed the existence of over 2,600 worlds beyond our solar system, and the data suggested something even more extraordinary. Nearly every star in the galaxy has at least one planet. Some have entire systems, just like ours. And it gets more specific than that. Data from Kepler suggests that roughly 1 in 4 red dwarf stars, the most common type of star in the Milky Way, has a rocky planet sitting in the habitable zone. That is the region around a star where temperatures are just right for liquid water to exist on the surface. Not too hot, not too cold. The kind of place where, at least as far as we understand it, life has a chance. Now multiply that by the sheer number of red dwarfs in the galaxy. There are tens of billions of them, which means there could be billions of potentially habitable worlds in the Milky Way alone, not in the entire universe, just in our galaxy. One galaxy among trillions. So here is the question that should keep you awake at night. Where is everyone? That question, asked casually over lunch in the summer of 1950, would become one of the most haunting puzzles in all of science. The man who asked it was Enrico Fermi, a physicist who had helped build the first nuclear reactor and who had a gift for cutting through complexity to find the sharp edge of a problem. He was at the Los Alamos National Laboratory, eating lunch with 3 colleagues, Emil Konopinski, Edward Teller, and Herbert York. The conversation had drifted to a recent cartoon in The New Yorker about aliens stealing public trash cans. They laughed about it. The topic moved to flying saucers, which were all over the news at the time. And then, seemingly out of nowhere, Fermi made a quick mental calculation. He considered the age of the galaxy, roughly 13 billion years. He considered the number of stars, hundreds of billions. He considered the likelihood that some fraction of those stars had planets, and that some fraction of those planets could support life, and that some fraction of that life could become intelligent, and that some fraction of that intelligence could develop technology. Even if you made every single one of those fractions extremely small, the numbers still came out enormous. There should be thousands, maybe millions of technological civilizations in the Milky Way. And then he asked the question, where is everybody? His colleagues remembered the moment clearly. There was a pause, and then Fermi began working through the math more carefully, estimating that even with relatively slow spacecraft, a civilization could colonize the entire galaxy in a few million years. That sounds like a long time, but compared to the age of the galaxy, it is nothing. It is a blink. If even one civilization had arisen 1 billion years before us and had started expanding, they would have had more than enough time to reach every corner of the Milky Way. They should be here. They should be everywhere. But they are not. And nobody has been able to explain why. This is the Fermi Paradox. Not a paradox in the strict mathematical sense, but a contradiction between what the numbers tell us should be true and what we actually observe. The numbers say the galaxy should be teeming with life. The sky says otherwise. 11 years after that lunch conversation, a young astronomer named Frank Drake tried to give the question some mathematical structure. It was 1961, and Drake was organizing the first scientific conference dedicated to the search for extraterrestrial intelligence at the National Radio Astronomy Observatory in Greenbank, West Virginia. He needed a way to frame the discussion, so he wrote an equation on the blackboard. The Drake equation is not really an equation in the way you might think of one. It does not give you a definitive answer. It is more like a way of organizing our ignorance. It takes the question of how many communicating civilizations might exist in the galaxy and breaks it down into 7 separate factors. You start with the rate at which new stars form in the galaxy. Then you multiply by the fraction of those stars that have planets. Then by the fraction of those planets that could support life. Then by the fraction where life actually appears. Then by the fraction where that life becomes intelligent. Then by the fraction that develops technology capable of sending detectable signals into space. And finally, you multiply by the average length of time such a civilization survives and sends those signals. When Drake first ran the numbers at that 1961 conference, using rough estimates for each factor, he came up with a number somewhere between 1,000 and 100 million civilizations in our galaxy alone. The room was electrified. Even with conservative assumptions, the galaxy should be crowded with voices. But there is a problem embedded in that equation. A quiet, devastating problem that would take decades to fully appreciate. We have been listening for those voices for over 60 years now, and we have heard nothing. The search for extraterrestrial intelligence, which most people know as SETI, began in earnest in 1960, when Drake himself pointed the 85-foot radio telescope at Greenbank toward 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani. He listened for artificial signals at the frequency of 1420 MHz, the natural emission frequency of hydrogen, the most abundant element in the universe. The logic was elegant. If you wanted to send a message to another civilization, you would choose a frequency that any scientifically literate species would already be monitoring. Hydrogen's frequency was the obvious choice, a cosmic common ground. Drake heard nothing. But that was just the beginning. Over the following decades, SETI programs expanded dramatically. The Big Ear radio telescope at Ohio State University ran the longest continuous SETI program in history, scanning the skies from 1973 to 1995. The Allen Telescope Array, a collection of 42 radio dishes in Northern California, was built specifically for SETI observations. The Breakthrough Listen project, launched in 2015 with $100 million in funding, became the most comprehensive search ever conducted, surveying the nearest million stars and the centers of 100 nearby galaxies. None of them found anything. Well, almost nothing. And that almost is important, because it introduces the first of many scientific puzzles that will follow us through this entire story. On the evening of August 15, 1977, the Big Ear telescope was scanning the skies as usual. The data was being recorded on a simple line printer, with each line showing the radio energy detected across 50 frequency channels. The numbers were averaged over 10-second intervals. Most of the time, the readings were low. Background noise, static from the cosmos. But on that particular evening, something different appeared. A signal arrived that was 30 times stronger than the background noise. It lasted for exactly 72 seconds, which was precisely the length of time the big ear could observe any single point in the sky as the Earth rotated beneath it. The signal was narrowband, centered almost exactly on the hydrogen frequency. It had all the characteristics that scientists had predicted an artificial extraterrestrial signal would have. It rose in intensity for 36 seconds, peaked, and then faded for 36 seconds, exactly matching the pattern you would expect from a stationary source being swept across by the telescope's beam. A few days later, a volunteer astronomer named Jerry Amon was reviewing the printed data. When he saw the signal's intensity sequence, 6 characters reading 6EQUJ5, he circled it in red ink and wrote a single word in the margin: "Wow." The WOW signal, as it became known, was the strongest candidate for an extraterrestrial communication ever detected. It came from the direction of the constellation Sagittarius. It appeared in one of the telescope's 2 feed horns, but not the other, which meant it was real, not internal interference. It matched every theoretical prediction for what an alien signal would look like. And then it was never heard again. Amon himself searched for it repeatedly in the months that followed. Other telescopes pointed at the same coordinates. Decades passed. The Breakthrough Listen project conducted targeted observations of the signal's origin point in 2022, using both the Green Bank telescope and the Allen telescope array. Nothing. One signal, one time, and then silence. For nearly 50 years, the WOW signal sat in a strange category of its own. Not confirmed, not explained, not repeated. It was the closest we had ever come to hearing another voice in the dark, and it vanished as quickly as it appeared. Recently, though, a team of researchers led by Abel Mendez at the University of Puerto Rico at Arecibo may have found an answer. While analyzing archived data from the now collapsed Arecibo Observatory, they discovered something unexpected. Between 2017 and 2020, the Arecibo telescope had detected multiple narrowband signals similar to the WOW signal at frequencies near the hydrogen line. They were fainter, but they shared the same basic characteristics. The team proposed that the WOW signal was not a message from another civilization, but a natural astrophysical event. Specifically, they hypothesized that a cold cloud of hydrogen gas in the line of sight had been briefly energized by a powerful burst of radiation from a background source, likely a magnetar flare or a soft gamma repeater. This would have caused the hydrogen cloud to brighten dramatically for a short period, producing exactly the kind of narrowband signal that the big ear detected. It is, in essence, a cosmic flashbulb. A magnetar screams, and a cloud of hydrogen briefly catches fire in radio waves. The alignment has to be precise. The cloud, the source, and the Earth all need to line up, which is why it happened once and was never seen again from the same spot. The researchers were careful to note that this does not definitively solve the mystery, but it is the most complete natural explanation proposed so far, and it accounts for every observed property of the signal. The SETI community, including some of the original Big Ear researchers, has accepted the explanation with something that looks a lot like relief, and maybe a little disappointment, because if the WOW signal was natural, then we are back to where we started. 60 years of listening, with the most sensitive instruments ever built, pointed at the most promising targets in the sky, and we have found nothing that we can confidently say came from another mind. The silence is not just notable, it is statistically screaming. Think about what that means. Our galaxy is roughly 13 billion years old. The first generation of stars formed within a few 100 million years of the Big Bang. Those stars lived and died and seeded the galaxy with heavy elements. Second and third generation stars formed from those enriched clouds, and around them, rocky, planets condensed. Conservative estimates suggest that Earth-like planets have been forming in the Milky Way for at least 10 billion years. Many of them are billions of years older than Earth. If life is common, and if intelligence is a natural outcome of evolution, then there should be civilizations out there that are not just thousands of years ahead of us, but millions or even billions of years ahead of us. Civilizations so advanced that their technology would be as incomprehensible to us as a smartphone would be to a trilobite. And yet, the sky is quiet. There is a concept in SETI research called radio leakage. It refers to the electromagnetic signals that a civilization unintentionally broadcasts into space. Television transmissions, radar pulses, military communications. Earth has been leaking radio signals since the 1930s. Those signals travel at the speed of light, expanding outward in an ever-growing sphere. Right now, our radio bubble extends roughly 90 light-years in every direction. Any civilization within that bubble, if they had sensitive enough receivers, could detect us. But here is the uncomfortable part. We have been detectable for less than a century. The galaxy is 100,000 light-years across. Our little bubble of noise is a tiny whisper in an enormous room. And if we can barely be heard, imagine how many other civilizations might be whispering right now, their signals too faint and too far away for our instruments to catch. Or imagine that they are not whispering at all. That is the question that splits the Fermi Paradox into two equally terrifying possibilities. Either the galaxy is empty, and we are alone in a way that is almost too vast to comprehend, or the galaxy is full of life, and something is keeping everyone quiet. The first possibility suggests that somewhere along the chain, from chemistry to civilization, there is a step so unlikely that it almost never happens. A bottleneck so narrow that out of all the billions of potentially habitable worlds in the Milky Way, only one, ours, managed to squeeze through. The second possibility suggests something darker, that the silence is not a sign of absence, but a sign of intent, that civilizations exist, but they have learned, perhaps through bitter experience, that making noise in the cosmos is a very dangerous thing to do. Both possibilities have names. Both have been studied extensively, and both lead to conclusions that, once you truly understand them, will change the way you look at the night sky. The first is called the Great Filter, and it may be the most important idea humanity has ever encountered, because the question is not whether the Great Filter exists. The math demands that it does. The question, the one that carries the weight of our entire future, is whether we have already passed through it, or whether it is still waiting for us somewhere up ahead. To understand why that matters, we need to go back to the very beginning, not the beginning of human civilization, not the beginning of life on Earth. We need to go back to the moment when the universe first became capable of producing the ingredients for life itself. Because it turns out that moment happened much more recently than most people realize, and the reasons why are deeply unsettling. The universe had to cook for a very long time before it could make anything as complicated as a living cell. The Big Bang produced hydrogen and helium and tiny traces of lithium. That was it. Every other element, every atom of carbon in your bones, every atom of oxygen in your lungs, every atom of iron in your blood, had to be forged inside a star and then scattered into space when that star died. It took generations of stars, living and dying and seeding the cosmos with their ashes, before the raw materials for rocky planets and organic chemistry existed in sufficient quantities. The first stars, the ones that formed from pure hydrogen and helium, were enormous, hundreds of times more massive than our Sun. They burned through their fuel in just a few million years and then exploded as supernovae, scattering the first batch of heavy elements into the surrounding gas. Those elements mixed into new clouds of gas, which collapsed to form the next generation of stars, slightly richer in metals. And those stars lived and died and enriched the cosmos further. Generation after generation, the chemistry of the universe slowly became more complex, but there was a catch. Not all elements are created equally. Some are abundant. Carbon and oxygen and nitrogen are relatively common products of stellar fusion, but others are rarer. And one of those rare elements turns out to be absolutely critical for life as we know it: phosphorus. It is the 17th most abundant element in the universe. That might sound high enough, but compared to the other 5 elements essential for biology, hydrogen, carbon, nitrogen, oxygen, and sulfur, phosphorus is the outlier. It is the least available of the 6 in Earth's oceans. It is the limiting nutrient for life in most marine ecosystems. Without it, you cannot make DNA. You cannot make RNA. You cannot make ATP, the molecule that every living cell uses as its energy currency. You cannot make the phospholipid membranes that form the boundary of every cell. And here is where the Fermi Paradox begins to tighten its grip. Phosphorus is produced primarily in supernova explosions, but the details of how it is produced are still not fully understood. Current models of galactic chemical evolution actually underpredict the amount of phosphorus we observe in our own solar system. Researchers recently discovered 15 unusual stars with abnormally high phosphorus abundances, and their chemical fingerprints do not match any known nucleosynthetic process. Something is making phosphorus that our theories cannot account for. Meanwhile, when scientists surveyed nearby stars using the Hypatia catalogue, a database of stellar chemical abundances, they found that phosphorus data exists for only about 1% of all catalogue stars and 1% of known exoplanet host stars. We simply do not know how much phosphorus most stars have. But what little data we do have suggests a troubling picture. Our Sun has relatively high phosphorus compared to many nearby stars. Planets forming around phosphorus-poor stars may never develop the chemistry needed for life, no matter how perfectly they sit in the habitable zone. This means the number of truly habitable worlds might be far smaller than the Drake equation suggests. The equation asks whether a planet can support liquid water, but it does not ask whether that planet has the right chemistry, and chemistry, it turns out, might be the real bottleneck. In 2023, data from the Cassini spacecraft revealed something remarkable about Enceladus, one of Saturn's icy moons. Plume samples from its subsurface ocean showed phosphate concentrations over 100 times higher than in Earth's oceans. Here was a world where phosphorus was abundant, locked away beneath miles of ice in a dark ocean that never sees sunlight. It was a reminder that the distribution of this critical element is wildly uneven, even within our own solar system. Some worlds are bathed in it. Others might be starved of it entirely. And this unevenness raises a question that the Drake equation never thought to ask. How many of those billions of habitable zone planets are habitable in theory, but barren in practice? How many have liquid water, but lack the chemical vocabulary to write even the simplest sentence? Of biology? The answer might be most of them, but phosphorus is only the first surprise, because the chemistry problem extends beyond any single element. Life requires not just the right atoms, but the right molecules, arranged in the right configurations, in the right environment, at the right time. And the gap between having the right ingredients and having the first living cell is so enormous that scientists have given it its own name. Abiogenesis, the emergence of life from non-living matter. We know it happened at least once because we are here. But how it happened remains one of the deepest unsolved mysteries in all of science. The simplest living cell is not simple at all. It requires a membrane to separate inside from outside, a way to store and copy information, a way to harvest energy, and a way to grow and divide. Each of those functions requires complex molecular machinery, and getting all of that machinery to emerge simultaneously from a soup of random chemicals is a problem so staggering that some researchers believe it may represent the single most improbable event in the history of the cosmos. We have theories. Alkaline hydrothermal vents on the ocean floor may have provided the right conditions, with natural chemical gradients that could have driven the first metabolic reactions. Warm acidic lakes rich in carbonates and phosphorus may have provided the crucible for early RNA chemistry. Lightning strikes in early atmospheres may have sparked the formation of amino acids, as Stanley Miller and Harold Urey demonstrated in their famous 1953 experiment. But none of these scenarios has produced life in a laboratory. We can make amino acids. We can make nucleotides. We can even coax RNA to self-replicate under carefully controlled conditions. But the gap between those individual molecular achievements and a functioning, self-sustaining, reproducing cell remains as wide as ever. Maybe life is easy. Maybe given the right conditions, it arises quickly and inevitably, the way crystals form in a cooling solution. If that is true, then the universe might be teeming with microbial life, and the great filter lies somewhere further along the chain. Or maybe life is hard. Maybe abiogenesis is the cosmic lottery, and Earth just happened to hit the jackpot in a game where the odds are so astronomical that it only happens once in an observable universe. We do not know which of those scenarios is true, and that uncertainty is itself a clue. Because if life were easy, we would expect to find signs of it by now. Mars, Europa, Enceladus. We have probed and scanned and sampled, and so far the results are tantalizing but inconclusive. No definitive biosignature, no confirmed microbial fossil, just hints and possibilities and the maddening quiet of worlds that might be alive or might be utterly, perfectly dead. And so the silence deepens. Look up again at the night sky. Count the stars. Know that behind each one there might be a world with liquid water and the right temperature and a rocky surface warmed by gentle sunlight. And know that none of those worlds, as far as we can tell, is calling out to us. The numbers say the galaxy should be alive with conversation. But the galaxy is not talking. And the distance between those two facts is where the real story begins. Because the question is no longer whether we are alone. The question is why we appear to be alone. And the answer, when you follow the evidence carefully and honestly, leads to places that are far more unsettling than simple emptiness. It leads to the great filter, and the great filter does not care about our feelings. In 1998, an economist named Robin Hanson sat down and tried to think about the Fermi Paradox the way an economist would, not with telescopes or radio dishes, but with probabilities and selection effects. He asked a simple question. If the universe is so old and so vast, and if life should be common, then what is preventing the galaxy from being visibly colonized? Something must be stopping civilizations from making it all the way from raw chemistry to interstellar expansion. Some step along the way must be incredibly, almost impossibly, hard. He called this step the Great Filter. The idea is deceptively elegant. Imagine the entire journey from lifeless planet to galaxy-spanning civilization as a long hallway with many doors. Each door represents a critical transition, the formation of a habitable planet, the emergence of simple life, the jump to complex cells, multicellularity, intelligence, technology, space colonization. The Great Filter is the idea that at least one of those doors is almost always locked. Almost every civilization that tries to walk this hallway gets stuck at the same point, unable to pass through. And the terrifying part is that we do not know which door is the filter. If the filter is behind us, if it is something that happened long ago in Earth's biological past, then we are the lucky ones. We are the rare species that somehow squeeze through the bottleneck. And the galaxy is silent because almost nobody else manages to make it this far. That is the optimistic reading. If the filter is ahead of us, if it is something that technological civilizations almost always run into and fail to survive, then our future is very dark indeed. It means that civilizations like ours arise regularly throughout the galaxy, reach roughly our level of development, and then are destroyed by something. Every time, without exception, to figure out where the filter might be, we need to look at the specific transitions in the history of life on Earth and ask which ones were genuinely hard, which ones required something so unlikely that it might only happen once in the history of a planet. Scientists call these hard steps, and the criteria for identifying them are specific. A hard step should be a singular event, something that appears to have evolved only once in the history of life on Earth. It should not be a convergent trait, the kind of feature that evolution invents over and over again independently, like eyes or wings or bioluminescence. Convergent traits are easy. Evolution finds them repeatedly because they are useful and the paths to them are many. But a singular event, something that happened exactly once and upon which all subsequent complexity depends, that is a candidate for the Great Filter. And there is one singular event in the history of life on Earth that stands above all others. Abiogenesis. For the first 2 billion years of life on Earth, roughly half the time life has existed on this planet, every living thing was a prokaryote. Simple, single-celled organisms without a nucleus, without internal compartments, without the complex molecular machinery that makes plants and animals and fungi possible. Bacteria and archaea. They were everywhere. They filled every niche from boiling hot springs to frozen Antarctic ice. They were spectacularly successful, but they were also, in a fundamental sense, stuck. Prokaryotes have a ceiling. Without a nucleus, they cannot maintain large, complex genomes. Without internal compartments, they cannot run multiple biochemical processes simultaneously. Without mitochondria, they cannot generate enough energy to grow large or complex. A bacterium can be cunning and versatile, but it will always be small and simple. It will never build a brain. It will never form a tissue. It will never think. And then, roughly 1.8 billion years ago, something extraordinary happened. An archaeal cell swallowed a bacterium, and instead of digesting it, the two organisms began to cooperate. The bacterium became an endosymbiont, living inside the archaeal cell and gradually transforming into what we now call a mitochondrion. This single event, one cell absorbing another and forming a permanent partnership, gave rise to the eukaryotic cell, the cell with a nucleus, the cell that would eventually produce every complex organism on Earth. But here is the part that should make you pause. This event appears to have happened exactly once in 3.7 billion years of biological history. Every eukaryote on Earth, every animal, every plant, every fungus, every protist, traces its ancestry back to that single merger. There is no second lineage, no alternative version of the eukaryotic cell that arose independently through a different path. In an evolutionary landscape where eyes have evolved independently over 40 times, and flight has evolved at least 4 times, the eukaryotic cell happened once. And it required an almost absurd alignment of conditions. 5 things had to come together simultaneously. First, chemiosmosis, the use of a proton gradient across a membrane to generate energy. This was the basic energy system inherited from the earliest life near alkaline hydrothermal vents, where natural chemical gradients provided free power. Second, phagocytosis, the ability of one cell to physically engulf another. Without this, the initial merger could never have happened. Third, endosymbiosis itself, not just engulfing, but coexisting. The swallowed bacterium had to survive inside its host, and the host had to tolerate the presence of the newcomer. This is not as common as you might think. Most of the time, when one cell engulfs another, it simply digests it. For the two to establish a permanent partnership requires an unlikely balance of biology and luck. Fourth, quantum electron tunneling. The captured bacterium, the protomitochondrion, used a remarkable molecular machine called complex Y that exploits quantum mechanics to shuttle electrons through a chain of iron-sulfur clusters. This allowed it to maintain the proton gradient far more efficiently than any system that had existed before, generating an enormous surplus of energy. And fifth, ATP synthase, a molecular turbine, literally a rotating mechanical engine at the nanoscale, that converts the proton gradient into ATP, the universal energy currency of all life. Each rotation of this tiny motor pumps out one molecule of ATP, and with enough ATP, the new eukaryotic cell could afford to be large. It could afford to maintain a complex genome. It could afford to build the molecular machinery for multicellularity and eventually intelligence. With mitochondria, eukaryotic cells had roughly 100,000 times more energy available than a typical prokaryote. They could grow 10,000 times larger. They could do things that no bacterium could ever dream of, if bacteria could dream. But it took 2 billion years for this to happen. 2 billion years of prokaryotic life, during which nothing remotely this complex emerged. That staggering delay suggests that eukaryogenesis is genuinely hard. Not just unlikely, but perhaps one of the most improbable events in the entire history of biology. And that delay has implications for the Fermi Paradox. Because if eukaryogenesis is the great filter, or at least one of the great filters, then it means that the universe could be absolutely teeming with microbial life, oceans of bacteria on billions of worlds, and yet complex life could be vanishingly rare. The jump from simple to complex might be the locked door in the hallway. But some scientists push back on this idea. In a series of papers published in 2024, paleobiologist Dan Mills and his colleagues at Penn State argued that the hard steps model has been championed primarily by astrophysicists and economists, while evolutionary biologists, the people who actually study these transitions for a living, have been largely disengaged from the conversation. Mills pointed out that what looks like a singular event might be an artifact of the fossil record. Lineages that independently evolved similar features might have simply gone extinct, leaving no trace. We see one origin of eukaryotes, not necessarily because it happened only once, but because only one lineage survived. Mills also noted that endosymbiosis is not as rare as the hard steps model suggests. We see it happening today in many biological contexts. Nitrogen-fixing bacteria in plant root nodules, algae living inside coral cells, bacterial endosymbionts that provide essential nutrients to insects. The process is recurring and widespread. What was unique about the origin of mitochondria might not have been the endosymbiosis itself, but the specific conditions that allowed one particular partnership to give rise to an entirely new domain of life. This is an important critique, and it remains unresolved. But even if eukaryogenesis turns out to be less improbable than it appears, there is another candidate for the great filter hiding in the early history of complex life. The oxygen catastrophe. Roughly 2.4 billion years ago, a group of cyanobacteria invented a new way to harvest energy from sunlight. Oxygenic photosynthesis. For the first time, organisms were splitting water molecules and releasing oxygen as a waste product. This was a revolutionary metabolic innovation, but it had a devastating side effect. Oxygen was toxic to almost every other form of life on the planet. Before photosynthesis, Earth's atmosphere had virtually no free oxygen. The planet was dominated by anaerobic organisms that thrived in a reducing environment. When oxygen began to accumulate, it was a catastrophe of unimaginable proportions. The organisms that could not tolerate oxygen died. Entire ecosystems collapsed. The oxygen catastrophe, also called the Great Oxidation Event, may have been the largest mass extinction in the history of life on Earth, dwarfing even the asteroid impact that killed the dinosaurs. An oxygenic photosynthesis, like eukaryogenesis, appears to have evolved only once. Every oxygen-producing organism on Earth today, from the smallest cyanobacterium to the largest redwood tree, inherits the same photosynthetic machinery from that single evolutionary innovation. One invention, one time. And it nearly sterilized the planet before it ultimately transformed it into a world where complex oxygen-breathing life could thrive. This raises a pattern that keeps repeating as we walk through the history of life. The transitions that opened the door to greater complexity were not gradual progressions. They were singular, improbable events, each one teetering on the edge of never happening at all. And each one was followed by vast stretches of apparent stasis, millions or billions of years where nothing much changed, as if the universe were catching its breath before the next unlikely leap. Consider what came after eukaryogenesis and the rise of oxygen. Multicellularity, the ability of individual cells to cooperate, specialize, and form a single organism with differentiated tissues. This has evolved independently in several lineages, which suggests it might not be a hard step, but true obligate multicellularity, the kind that produces large, complex organisms with organs and nervous systems, appears only in a handful of lineages, and it took over 1 billion years after eukaryotes first appeared for the Cambrian explosion to produce the riot of animal body plans that populate the fossil record. The Cambrian explosion itself is a puzzle. Around 541 million years ago, almost every major animal body plan appeared in the fossil record within a span of roughly 20 million years. That is a geological eye blink. Something triggered an avalanche of biological innovation, and researchers are still debating what it was. One 2024 study linked it to the onset of modern plate tectonics, which may have created new environmental niches and chemical conditions that favored complex organisms. Another line of research connects it to rising oxygen levels crossing a critical threshold that allowed large, energy-hungry animals to survive. Whatever caused it, the Cambrian explosion was a one-time event on Earth. There was no second explosion, no repeat performance. Complex animal life appeared once, in a burst, and then evolution spent the next 500 million years elaborating on those original blueprints. Each of these transitions, abiogenesis, eukaryogenesis, photosynthesis, multicellularity, the Cambrian explosion, represents a potential filter, a place where the path to intelligence could have been permanently blocked. And the fact that each one took so long, that billions of years were required for each leap, suggests that the chain from lifeless rock to thinking creature is not an inevitable march of progress. It is a tightrope walk over an abyss, with each step less certain than the last. And yet, even after the Cambrian explosion, the road to intelligence was anything but guaranteed. Consider this. Dinosaurs ruled the Earth for over 165 million years. That is roughly 800 times longer than modern humans have existed. They were spectacularly successful, filling every ecological niche from ocean depths to open skies. Some of them were large-brained. Some showed signs of social behavior and even problem-solving. But in all that time, not one lineage of dinosaurs developed technology. Not one built a fire or carved a tool or wondered about the stars. It took an asteroid impact, the Chicxulub event, 66 million years ago, to clear the stage. The dinosaurs were wiped out, and the small, furry mammals that had been hiding in their shadows were suddenly handed the keys to the planet. Without that random, catastrophic intervention from space, mammals might still be rat-sized, creatures scurrying through the underbrush. There would be no primates, no hominids, no human civilization, no one to ask where everybody is. And this suggests something uncomfortable about intelligence. It is not an inevitable outcome of evolution. It is not the destination that all complex life is marching toward. It is a fluke, a lucky break that required a very specific sequence of catastrophes and recoveries, played out over hundreds of millions of years, on a planet that happened to have exactly the right conditions at exactly the right moments. Think about what intelligence requires from a purely biological perspective. You need a large, energy-hungry brain. The human brain consumes roughly 20% of the body's total energy budget, despite being only about 2% of its mass. That is an enormous cost. Most animals cannot afford it, and evolution tends to be ruthless about eliminating expensive features that do not provide an immediate survival advantage. For most of Earth's history, being smart was not particularly useful. Being fast or strong or venomous or well camouflaged was far more practical. Something had to change in the environment to make big brains worth the investment, and researchers are still debating what that something was. Climate change in East Africa, which drove our ancestors out of the forests and onto the open savanna. The social complexity of primate groups, which rewarded individuals who could navigate alliances and predict behavior. The invention of cooking, which allowed us to extract more calories from food and feed our growing brains. Each of these factors played a role, but none of them was guaranteed. Change any one of them, subtract the asteroid, shift the climate, alter the geography, and the chain breaks. Intelligence does not emerge, and a planet that is teeming with complex life continues to orbit in silence, beautiful and biologically rich and utterly voiceless. This is one of the most sobering implications of the Great Filter. Even if a planet manages to produce complex multicellular life, even if it develops diverse ecosystems and sophisticated organisms, it might never produce a species that builds telescopes and wonders about its place in the cosmos. Intelligence might be the rarest commodity in the universe, and technology might be rarer still, because there is one more step between intelligence and detectability. A species can be smart, even brilliant, and still leave no trace that astronomers on another world could detect. Dolphins are intelligent, crows use tools, octopuses solve puzzles and escape from sealed containers, but none of them produces radio signals. None of them lights up the infrared spectrum with waste heat from their cities. From the perspective of a civilization scanning the sky 1,000 light-years away, a planet full of dolphins is indistinguishable from a planet with no intelligent life at all. The step that makes a species detectable is not intelligence itself. It is the specific, narrow form of intelligence that leads to technology, and specifically, technology that manipulates electromagnetic radiation, radio, light, heat, the signals that travel across the void at the speed of light and can be picked up by sensitive instruments. That is an extraordinarily specific capability, and it is not clear that evolution naturally selects for it. On Earth, it required a chain of improbable developments stretching from the control of fire, to the invention of writing, to the discovery of electromagnetism, to the construction of radio transmitters. Each step built on the ones before it, and at any point, the chain could have broken. Paleobiologist Ole Vinn has recently proposed that the Great Filter might exist specifically at the transition between intelligence and sustainable technological civilization. He argues that intelligent biological organisms carry inherited behavior patterns, deep evolutionary drives like tribalism, short-term thinking, and resource hoarding that served them well in their evolutionary past, but become existentially dangerous once they gain the power to alter their planet's climate, build nuclear weapons, or create artificial intelligence. The filter, in this view, is not that civilizations cannot build technology. It is that they cannot survive it. This is the version of the Great Filter that hits closest to home, because it describes us. But before we follow that thread too far, there is one more piece of this puzzle that makes the Great Filter even more troubling, and it comes not from the deep past, but from the present sky. In 2015, a citizen science group called Planet Hunters, sifting through data from the Kepler Space Telescope, flagged a star that was behaving in a way nobody had ever seen before. The star was KIC 462852, an otherwise ordinary yellow-white dwarf about 1,470 light-years from Earth, in the constellation Cygnus. It was dimming, not in the gentle periodic way that indicates a planet passing in front of it, but erratically, unpredictably, and by enormous amounts, sometimes by 1%, sometimes by as much as 22%. No planet could do that. A Jupiter-sized world passing in front of a sun-like star blocks roughly 1% of its light. To block 2%, you would need something vastly larger, and the dips were not regular. They came and went without pattern, at different depths and durations. The star became known as Tabby's star, named after astronomer Tabitha Boyajian, who led the initial study. And for a brief, electrifying moment, some scientists speculated that the dimming could be caused by an alien megastructure, a Dyson swarm perhaps, a vast collection of energy-harvesting satellites encircling the star, built by a civilization far more advanced than our own. Subsequent observations have made that explanation unlikely. Researchers found that the dimming was more pronounced in ultraviolet light than in infrared, which means the blocking material is not a solid structure, but something more like fine dust. Current theories suggest that dimming is caused by circumstellar debris, possibly from an evaporating exomoon being torn apart by the star's gravity. A 2019 study from Columbia University proposed a model where the long-term fading is caused by chunks of a captured exomoon's dusty outer layers accumulating in a disk around the star. But no single model fully explains every aspect of Tabby's star's behavior. And in 2019, astronomers identified 21 additional stars that exhibit similar erratic dimming. Whatever is happening at Tabby's star, it is not unique. It is a class of phenomenon, and we do not fully understand it yet. Is it natural? Almost certainly. But the fact that our first reaction was to wonder whether it might be artificial tells us something important about where we are in this story. We are looking for signs of others. We are desperate for them. And every time the universe offers us an anomaly, a signal that does not quite fit, a star that does not quite behave, we lean forward in our seats and hold our breath, because we know, somewhere deep in our bones, that the silence of the cosmos is not normal. Something is wrong with the numbers, and the great filter, wherever it lies, is the most mathematically honest explanation for why. But what if the filter is not biological at all? What if the real barrier is not about evolving intelligence, but about what intelligent civilizations do once they exist? That possibility leads us into much darker territory. A hypothesis about the nature of survival itself in a universe where resources are finite and trust is impossible. A hypothesis that imagines the cosmos not as an empty void, but as a dark forest filled with predators. Imagine the universe as a forest at night, endless, dark, impossibly vast, and you are walking through it. You have no map. You have no light. You can hear the wind moving through branches overhead, but you cannot see what is moving out there in the shadows. You know the forest is old. You know others have walked through it before you, but you cannot see them, and you cannot hear them. And here is the question that changes everything. Are they silent because they are gone? Or are they silent because they know something you do not? This is the essence of the dark forest hypothesis, a proposed solution to the Fermi Paradox that takes the question of cosmic silence and turns it into something far more sinister than simple absence. In this model, the galaxy is not empty. It is full of civilizations, some ancient and vast beyond imagining. But they are all hiding, every single one. Because in this universe, the penalty for being heard is death. The hypothesis was formalized by Chinese science fiction writer Liu Cixin in his 2008 novel, The Dark Forest, the second book in his Remembrance of Earth's Past trilogy. But the underlying logic had been explored by others before him, including astrophysicist David Brin in a 1983 paper. What Liu did was crystallize the idea into a framework so rigorous and so chilling that it has become one of the most widely discussed explanations for the Fermi Paradox among both scientists and the general public. The framework begins with two axioms. These are not assumptions about biology or technology. They are axioms about the fundamental nature of survival in a universe with finite resources. Axiom 1. Survival is the primary need of every civilization. This is not a moral statement. It is a description of reality. A civilization that does not prioritize its own survival ceases to exist. The ones that remain are, by definition, the ones that survived. Axiom 2. Civilizations continuously grow and expand, but the total matter and energy in the universe remain constant. Resources are finite. And in the long run, every expanding civilization will eventually compete with others for those resources. From these two axioms, Liu derives a devastating conclusion through the concept he calls the chain of suspicion. Here is how it works. Imagine civilization A discovers civilization B. They detect a radio signal, or they notice an anomaly in a distant star's light curve, or they find evidence of industrial activity in an exoplanet's atmosphere. Civilization A now has a choice: contact B, ignore B, or destroy B. The rational thing might seem to be contact, communication, diplomacy. But consider the problem from A's perspective. A does not know anything about B's intentions. B might be friendly, B might be hostile, B might be indifferent. And A has no way to verify which of those is true, because any message B sends could be a lie. A friendly greeting could be a trap. A promise of peace could be a ploy to buy time. But it gets worse. Even if A somehow determines that B is currently friendly, A cannot know what B will be like in the future. Civilizations change. They grow. They experience technological explosions, sudden leaps in capability that are impossible to predict. A civilization that is harmless today might, in a century or a millennium, develop weapons that could annihilate A's entire star system. And B faces the same uncertainty about A. This creates a recursive loop of suspicion that cannot be broken by any amount of communication. A does not know B's intentions. B does not know A's intentions. I does not know whether B knows A's intentions. B does not know whether A knows B's intentions. The chain extends infinitely, and at no point does trust become rational, because the cost of being wrong is extinction. The conclusion is stark. In a universe governed by these axioms, the only safe strategy is silence. Do not broadcast your existence. Do not reveal your location. And if you discover another civilization, destroy it before it can discover you. Because if you wait, if you hesitate, if you attempt communication, you are gambling your entire species on the hope that the stranger in the dark is friendly. And in a dark forest, hope is a luxury that no hunter can afford. This is a horrifying idea, and it is supposed to be. But before we dismiss it as science fiction, we need to reckon with the fact that the dark forest hypothesis makes a very specific prediction that happens to match what we observe. If the galaxy is a dark forest, then the sky should be silent. Civilizations should not be broadcasting. They should not be building megastructures that alter their stars' light curves. They should not be colonizing visibly. They should be hiding. And the silence of the cosmos is exactly what we would expect to see from the inside of a dark forest. That does not make it true, but it does make it worth taking seriously. And it adds a new dimension to some of the anomalies we have already discussed. Consider the wow signal again through the lens of the dark forest. In 1977, a powerful narrow-band signal appeared at the hydrogen frequency, lasted exactly 72 seconds, and was never detected again. We discussed the natural explanation, that it was likely a hydrogen mesa flare triggered by a magnetar. But for decades before that explanation was proposed, the signal sat in a category of its own, a single, unrepeated burst that matched every prediction for an artificial transmission. In the dark forest framework, that profile is suggestive, not of a civilization trying to communicate, but of a civilization making a mistake, a momentary slip, a signal that was not supposed to be sent, or that was sent before the sender realized the danger. One broadcast immediately silenced, followed by decades of absolute quiet from the same coordinates. It is probably not that. The natural explanation is more parsimonious, and Occam's razor favors it. But the dark forest adds an unsettling layer to the story. In a universe where broadcasting your location invites destruction, a single unrepeated signal is exactly what a mistake would look like. And it is not the only anomaly that gains a darker shade in this light. The fast radio bursts are another puzzle worth mentioning here. These are millisecond-long flashes of radio energy that arrive from extragalactic distances, carrying enormous power. Some repeat, most do not. They were first detected in 2007, and as of the mid-2020s, hundreds have been catalogued. The leading explanation is that they are produced by magnetars, highly magnetized neutron stars that can release stupendous amounts of energy in brief bursts. But some researchers, notably Avi Loeb at Harvard, have explored whether certain fast radio bursts could be consistent with the energy signatures of light sails being propelled by powerful directed energy beams. This is speculative, and it is important to say so clearly. The vast majority of scientists believe fast radio bursts are natural phenomena, but the very fact that their properties overlap with what you might expect from advanced propulsion technology means they sit in an uncomfortable zone. Not evidence of aliens, but not something we can fully explain either. The dark forest would say that if those bursts were artificial, they would be the exhaust flares of civilizations moving through space as quickly and quietly as possible. Not communications, not beacons. Just the unavoidable side effects of flight, visible only for a fraction of a second before the source vanishes back into the dark. But the dark forest hypothesis has serious critics, and their objections deserve a fair hearing. The most fundamental criticism is that the hypothesis assumes the universe is, well, dark, that civilizations are naturally hidden from one another and must actively reveal themselves to be detected. But this may not be true. An advanced civilization with powerful enough telescopes could survey every star in its galaxy and determine which ones have planets with biosignatures. No communication required, no signals needed, just observation. And if a civilization can see you whether you broadcast or not, then silence buys you nothing. This is the argument that economist Noah Smith made in a widely read 2024 critique. If the galaxy's most advanced civilizations can detect your atmospheric composition from across the galaxy, then hiding is not a viable strategy. The dark forest only works if the forest is genuinely dark, if there are real limits on how far and how clearly civilizations can see. And it is not clear that those limits exist for a civilization millions of years more advanced than ours. Game theory offers another objection. The dark forest assumes that preemptive strikes are always rational. But game theory shows that in iterated interactions, where the same players encounter each other repeatedly over long timescales, cooperation tends to emerge as the dominant strategy. Civilizations that learn to cooperate gain access to shared knowledge, shared resources, and mutual defense. Civilizations that always shoot first eventually run out of allies and face the universe alone. Over the timescales the dark forest considers, billions of years, the cooperators should outcompete the destroyers. And then there is the resource argument. The dark forest's second axiom states that resources are finite and must be competed for. But a civilization advanced enough to travel between stars is almost certainly advanced enough to harvest energy and materials from uninhabited systems. Asteroids, gas giants, brown dwarfs, rogue planets. The galaxy is full of resources that no one is using. The motivation for destroying another civilization's homeworld, risking counterattack and the wrath of unknown observers, seems far weaker when you can simply mine the asteroid belt of a neighboring system in peace. These critiques do not kill the dark forest hypothesis, but they do wound it. And they point to a deeper truth about the Fermi Paradox itself. No single explanation feels satisfying. The silence is too complete, too profound, to be explained by any one idea. Maybe the great filter and the dark forest are both partially right. Maybe the biological hurdles thin the field so dramatically that only a handful of civilizations arise in any given galaxy. And of those few, the dark forest dynamics ensure that the survivors stay hidden, creating a galaxy that appears empty from the perspective of a newcomer like us. But even this combination does not fully account for what we observe, because there is another line of evidence that suggests the problem is not just about biology or sociology. It is about physics. The laws of thermodynamics, the most fundamental rules governing energy and matter in the universe, impose hard limits on what any civilization can do. And when we go looking for signs that those limits have been reached or pushed against, we find something extraordinary. We find nothing, absolutely nothing, and that nothing might be the most important data point we have. Let me explain what I mean by that, because the scale of this emptiness is difficult to grasp. In the 1960s, a physicist named Freeman Dyson proposed a thought experiment that would reshape the search for extraterrestrial intelligence. Dyson reasoned that any civilization that continues to grow will eventually need more energy than a single planet can provide. The next logical step would be to capture the energy output of its entire star. You could do this by surrounding the star with a swarm of collectors, vast solar panels orbiting at various distances, intercepting starlight and converting it into usable power. This is the Dyson sphere, or more accurately, the Dyson swarm, since a rigid shell around a star is structurally impossible. The swarm would not need to be a single object. It could be trillions of individual collectors, each one modest in size, but collectively intercepting a significant fraction of the star's light. And here is the key insight that Dyson recognized. The second law of thermodynamics says you cannot use energy without producing waste heat. The collectors absorb sunlight and do useful work with it, but the energy that is not captured, and the waste heat from the work itself, must be radiated back into space. And it would be radiated at a much longer wavelength than the original starlight. Instead of visible light, the waste heat would glow in the mid-infrared part of the spectrum. This means a Dyson swarm would have a distinctive signature. The star would appear dimmer in visible light because the collectors are blocking some of it, but brighter in infrared because the waste heat is being radiated outward. You would see a star that looks like it is wearing a warm blanket, and if a civilization went further, if it expanded from one star system to many, eventually colonizing its entire galaxy, the effect would be enormous. An entire galaxy dimmed in visible light, but glowing in infrared. A galaxy wearing a blanket. Dyson proposed this not as a prediction of what aliens would definitely build, but as a way to search for them. If advanced civilizations exist, and if they use energy on stellar scales, then their waste heat should be detectable with infrared telescopes. You do not need to intercept their communications. You do not need them to be broadcasting. You just need them to exist and to use energy. The second law of thermodynamics does the rest. This is the beauty of what scientists call Dysonian SETI. It searches not for deliberate signals, but for the unavoidable physical consequences of technology. It is, in a sense, looking for footprints rather than voices. And in 2014, a team of astronomers at Penn State decided to follow those footprints on the largest scale ever attempted. The project was called GHAT, which stands for Glimpsing Heat from Alien Technologies. It was led by astronomer Jason Wright and funded by a grant from the John Templeton Foundation. The idea was straightforward but ambitious. Using data from the WISE satellite, the Wide Field Infrared Survey Explorer, which had surveyed the entire sky in mid-infrared wavelengths, the team would examine the infrared signatures of roughly 100,000 galaxies. They were looking for any galaxy that showed an unusual excess of mid-infrared radiation, the kind of excess you would expect if a significant fraction of its starlight was being intercepted and re-radiated as waste heat. Think about what that means. They were not looking for single civilizations around single stars. They were looking for galaxy-spanning super-civilizations. Kardashev typed the theory. Cultures that had colonized an entire galaxy and were using the energy of billions of stars. If Michael Hart's argument was correct, that any civilization capable of interstellar travel should eventually colonize its entire galaxy within a few million years, then some of those 100,000 galaxies should show signs of it. The results were published in a series of papers between 2014 and 2016, and the results were devastating for anyone hoping the galaxy is crowded. Of the roughly 100,000 galaxies examined, not a single one showed the infrared signature of a Kardashev-type Thur civilization using more than 85% of its starlight. The researchers were able to rule out galaxy-spanning civilizations at that energy level across the entire sample. For many galaxies, they could push the limit lower to around 50%. And for some galaxies with very little natural dust, galaxies where any artificial infrared excess would be especially easy to spot, they could go lower still. The sky was clean. This was not just an absence of evidence. It was evidence of absence, at least at the larger scales. If civilizations routinely expand to fill their galaxies, if the chain from intelligence to interstellar colonization is a natural progression, then the infrared sky should show it. WISE had the sensitivity to detect it, and it was not there. The GHAT team was careful to note the limitations of their search. Dust, the natural byproduct of dying stars and forming planets, produces its own infrared glow, and it can be difficult to distinguish from artificial waste heat. Their results were strongest for the most extreme scenarios. Galaxies completely dominated by technology. Smaller civilizations, those using only a few % of their galaxy's starlight, would be lost in the noise, and civilizations that had found ways to radiate their waste heat at very low temperatures would be essentially invisible. But even with those caveats, the GHAT results told a clear story. Whatever is going on in the universe, it does not include galaxy-spanning mega-civilizations glowing like infrared bonfires. The kind of future that optimists imagined, where intelligence inevitably leads to expansion, and expansion inevitably leads to visible transformation of the cosmos, does not appear to be happening. And the emptiness does not stop at galaxies. More recently, the VLA Sky Survey, using the Very Large Array of Radio Telescopes, surveyed over 950,000 unique pointings across the sky, searching for artificial radio transmissions at power levels ranging from 10 to the 11th to 10 to the 16th watts. For context, the most powerful directed energy beam that humanity could currently build would fall within that range. If another civilization in our galaxy were broadcasting at those power levels, the VLA should have detected it. It detected nothing. Let that sink in. Nearly 1 million directions. Sensitivity to transmissions that a moderately advanced civilization could produce, and not a single candidate signal. The thermodynamic argument cuts even deeper than the biological one, because it does not depend on assumptions about how life evolves or how civilizations behave. It depends only on physics. If you exist, and if you use energy, you produce waste heat. And if you produce waste heat, you should be detectable. This is not about intent. It is not about whether civilizations choose to be visible. It is about whether the laws of physics allow them to be invisible. And the answer, at least at the scales we have searched so far, is that nobody is there. This is where the various threads of the Fermi Paradox begin to weave together into something truly unsettling. The biological filters thin the field. The dark forest dynamics keep the survivors hidden. And the thermodynamic constraints suggest that even civilizations that are hiding cannot hide perfectly. Not if they are using energy on any significant scale. The combined weight of these observations pushes us toward a conclusion that is difficult to accept but increasingly hard to avoid. Either the galaxy is genuinely empty of advanced technological life, or advanced civilizations hit a ceiling far lower than we imagined. Not a ceiling of ambition or capability, but a ceiling imposed by the universe itself. A thermodynamic wall. The laws of physics do not just enable civilization, they also limit it, and those limits might be tighter than anyone expected. Perhaps every civilization that reaches a certain level of energy consumption discovers the same truth. That expansion has a cost, that the universe's resources, while vast, are not infinite, that every joule of energy used brings you one step closer to a boundary beyond which growth becomes not just difficult, but physically impossible. And that the civilizations we are looking for, the galaxy-spanning empires and Dyson-building supercultures, were never realistic in the first place. Perhaps the future of intelligence in the cosmos is not expansion. Perhaps it is contraction, efficiency, doing more with less, and perhaps a civilization that has mastered that art looks nothing like what we expect. It does not glow in the infrared. It does not broadcast radio signals. It does not build megastructures. It sits quietly, using only what it needs, a closed thermodynamic loop that produces almost no waste heat and leaves almost no trace. If that is true, then the silence of the cosmos is not a sign that nobody is home. It is a sign that everyone who survives has learned the same lesson. Be small, be quiet, be efficient, or be gone. But there is one more possibility that we have not yet considered, and it is in some ways the most extraordinary of them all. What if we are not late to the party? What if we are not surrounded by ancient civilizations that have learned to hide? What if the reason we see nothing when we look at the sky is not that the others are hiding, and not that they have been filtered out, but that they do not exist yet? What if we are the first? That idea sounds arrogant at first. Humans, the first intelligent species in a galaxy of 400 billion stars. The first technological civilization in a universe that has been churning out stars and planets for over 13 billion years. It seems absurd. It seems like the worst kind of cosmic narcissism. But the math does not care about our humility. In 2016, Harvard astrophysicist Avi Loeb and his colleague Rafael Batista published a paper that approached the habitability of the universe from a cosmological perspective. They asked a deceptively simple question. When, in the entire history of the cosmos, is life most likely to appear? The answer was not what most people expect. Loeb and Batista considered the full timeline of the universe, from the Big Bang to the far future. They looked at the rate of star formation, the types of stars being formed, the enrichment of the interstellar medium with heavy elements, and the lifetime of different stellar types. And they found that the single most important factor in determining when and where life can arise is not the age of the universe or the abundance of planets. It is the lifetime of the host star. Our Sun is a G-type star, a yellow dwarf, moderately massive and moderately bright. It has a total lifespan of roughly 11 billion years, of which about 4.5 billion have already passed. That gives Earth another 6 billion years or so, before the Sun begins to expand into a red giant and renders our planet uninhabitable. In cosmic terms, our Sun is relatively short-lived, but the most common type of star in the galaxy is not like our Sun. The most common stars are red dwarfs, M-type stars with less than half the mass of the Sun and a fraction of its brightness. They are dim and small and unremarkable, but they have one extraordinary property. They last forever. Not literally forever, but close enough. A red dwarf with 1/10 the mass of our Sun will burn its hydrogen fuel so slowly that it can shine for 10 trillion years. That is roughly 700 times the current age of the universe. The universe is 13.8 billion years old, and these tiny stars will still be burning when it is 10 trillion years old. They are the long-burning candles of the cosmos, and they are everywhere. Red dwarfs make up roughly 70 to 80% of all stars in the Milky Way. Proxima Centauri, the nearest star to our Sun, is a red dwarf. 20 of the 30 nearest stars to us are red dwarfs. Data from the Kepler telescope suggests that roughly 1 in 4 red dwarfs has a rocky planet in its habitable zone. Loeb and Batista ran the numbers on all of this and reached a striking conclusion. The probability of life emerging in the universe is not concentrated in the present era. It is overwhelmingly concentrated in the far future, around low-mass stars that have not yet reached the peak of their hospitable lifetimes. In fact, the probability of life is roughly 1,000 times higher in the distant future than it is today. Read that again. 1,000 times higher. We are not at the peak of cosmic habitability. We are at the very beginning of it. This means that if you were to randomly sample all the life that will ever exist in the universe, the vast majority of it has not been born yet. It will arise trillions of years from now, on rocky worlds orbiting dim red stars, in an era when the universe is old and cold and quiet, an era when our Sun has long since burned out and the Milky Way has merged with the Andromeda galaxy, and the night sky is utterly different from anything we would recognize. From this perspective, life on Earth is not late. It is staggeringly early. Loeb himself has used the word premature. We are here at the very beginning of the cosmic story, in the first chapter of a book that will run for trillions of pages. And if we are early, then the Fermi Paradox dissolves. There is no mystery about why the galaxy is silent. The other civilizations that will eventually arise simply do not exist yet. We are not surrounded by ancient cultures that are hiding or that have been filtered out. We are the first ones at a party that has barely started. But this explanation, elegant as it is, comes with its own weight of implications. And those implications are not comforting. Because if we are the first, then there is no one to help us. There is no elder civilization waiting in the wings to share its knowledge, to warn us about the mistakes it made, to hand us the blueprints for sustainable interstellar travel. There is no galactic federation, no cosmic internet, no benevolent alien intelligence watching over our development. We are alone in the most literal sense. The road ahead is uncharted, and there is no one who has walked it before us. Every mistake we make will be original. Every crisis we face will be unprecedented, and every solution we find will be ours alone. That is a terrifying thought, but it is also, in a strange and fragile way, a beautiful one, because it means that what we do matters. Not just to us, not just to our planet, but to the future of life in the universe itself. If we survive, if we learn to navigate the challenges of our own technology, and our own nature. We will be the ancestors of everything that comes after, the first light in a cosmos that has been dark since the beginning. But the if in that sentence is doing enormous work, because the obstacles between here and there are real, and they are formidable. And to understand just how formidable they are, we need to talk about the element that started this whole investigation: phosphorus. We discussed earlier how phosphorus is the rarest of the 6 elements essential for life, how it is produced in supernova explosions through processes that our models still do not fully understand, how our Sun has unusually high phosphorus compared to many nearby stars, and how the Hypatia catalogue shows that phosphorus data exists for barely 1% of known stars. But there is a deeper implication buried in those facts, one that connects directly to the question of whether we are early. Phosphorus is a product of stellar nucleosynthesis. It is made when massive stars explode. Each generation of stars enriches the interstellar medium with a slightly higher concentration of heavy elements, including phosphorus. This means the abundance of phosphorus in the galaxy has been increasing over time. The earliest stars had almost none. The stars forming today have more. And the stars that will form billions of years from now will have even more. If phosphorus is a limiting factor for the chemistry of life, and if its abundance has been increasing over cosmic time, then it follows that the conditions for life have been getting progressively better as the universe ages. The early universe might have had plenty of habitable zone planets, but those planets might have lacked the phosphorus needed to build DNA. The biochemical prerequisites for life were simply not in place yet. This aligns perfectly with Loeb's model. The universe is becoming more hospitable to life, not less. We are not living in the golden age of cosmic biology. We are living in the dawn. The best is yet to come, and it will come on a timescale that makes human history look like the first tick of a clock. But it also means something else, something that tightens the noose of the Fermi Paradox rather than loosening it. If we are among the first civilizations to arise, and if the conditions for life are only now reaching the threshold where complex biochemistry becomes possible, then the great filter that we discussed earlier might not be behind us at all. It might be a filter that is applied to the universe as a whole, not just to individual planets. The filter was not biological, it was chemical. The cosmos itself was not ready for life until very recently, and we happen to be one of the first planets to reach the threshold. This is known as the cosmic timing argument, and it has been gaining traction among astrobiologists in recent years. The idea is that the Fermi Paradox is not evidence of a filter that destroys civilizations. It is evidence that civilizations have not had time to arise yet. The universe is still young, in the only sense that matters, the sense measured not in years, but in the accumulation of the heavy elements that make complex chemistry possible. Consider one more piece of evidence that supports this view. In 2020, a team of researchers discovered 15 stars with abnormally high phosphorus abundances. These phosphorus-rich stars had chemical fingerprints that did not match any known nucleosynthetic pathway. Something was producing phosphorus in quantities that our models could not account for. The researchers speculated that advanced nucleosynthesis in convective reactive regions within massive stars, or the effects of stellar rotation, might be responsible. But the truth is that we do not fully understand where our own galaxy's phosphorus comes from. This is extraordinary. One of the 6 elements essential for life, and we do not know how it is made. The universe is keeping secrets from us, and those secrets might hold the key to understanding why we are alone. But the phosphorus mystery is just one thread in a much larger tapestry, Because phosphorus is not the only thing the early universe lacked. Molybdenum, a trace element that is essential for the enzymes that fix nitrogen, a process without which most life on Earth could not function. Molybdenum is produced primarily in the explosions of very massive stars, and its abundance in the galaxy has been increasing over time. Selenium, another trace element critical for biology, involved in protecting cells from oxidative damage, also produced in supernovae, also increasingly abundant over cosmic time. Iodine, zinc, copper. The list goes on. The universe is a factory that has been gradually building up its inventory of biochemically important materials, and the shelves are only now starting to be fully stocked. Taken together, this evidence paints a picture that is both humbling and strange. The universe spent over 13 billion years preparing the stage, cooking the elements, distributing them through generations of stars, building up the chemical complexity needed for biology to begin. And we are among the first actors to walk onto that stage, not the last, not the only, but possibly among the very first. And that changes the nature of the Fermi Paradox completely. It is no longer a question of where everyone is. It is a question of when everyone will be. The silence of the cosmos is not a sign of death. It is a sign of youth. But being young is not the same as being safe. Being first does not protect you from the challenges that every civilization must eventually face. And if the Great Filter teaches us anything, it is that the journey from here to there, from a single world to a lasting presence among the stars, is littered with the wreckage of possibilities that never quite made it. So where does that leave us? We are a species that has existed for roughly 300,000 years. We have had technology for perhaps 10,000. We have had radio for about a century. We have had nuclear weapons for 80 years. We have had the ability to alter our planet's climate for about half a century. And we have had artificial intelligence for less than a decade. Each of those capabilities came with risks that our evolutionary heritage did not prepare us for. We are creatures of the savannah, with brains wired for tribal politics and immediate rewards, wielding powers that can reshape the planet or destroy it. The mismatch between our ancient instincts and our modern capabilities is the most dangerous thing about us. It is the filter that Ole Vin warned about. The inherited behavior patterns that served our ancestors on the African plains may be the very things that destroy us in the nuclear age. And this is the part of the story where the Fermi Paradox stops being an abstract intellectual puzzle and becomes personal. Because if we are among the first, then the question of whether intelligence can survive its own technology is not academic. It is the most urgent question our species has ever faced. And the answer has not been determined yet. We are the experiment, and the experiment is still running. Look at the night sky one more time. See the stars. Know that some of them might one day harbor life, millions or billions of years from now, when the chemical conditions are finally right. Know that those future civilizations, if they ever arise, might look back at this moment in cosmic history and wonder about us, the first ones, the pioneers, the species that either figured it out or did not, and know that right now, tonight, the universe is holding its breath, because the next chapter of this story has not been written yet, and we are the ones who will write it. Or we will be the cautionary tale that someone else tells, trillions of years from now, about a promising young species that burned too bright and too fast, like a match struck in the dark. There is a deep irony embedded in the Fermi Paradox that most discussions miss. We spend so much time asking where the aliens are that we forget to ask the more important question. Where will we be? The answer depends on what we do next. And the universe is not going to give us any hints, because if we are the first, there are no hints to give. Only silence, only the dark, and us, floating on a small rock around an ordinary star, in a galaxy that may one day be home to civilizations beyond our imagining. But only if the first one, ours, manages to survive long enough to light the way. And that is not a guarantee. It has never been a guarantee. The Great Filter does not promise that anyone makes it through. The dark forest does not promise that silence means safety. The thermodynamic wall does not promise that efficiency equals survival. All they promise is that the universe plays for keeps, and the clock is ticking. But here is the thing about clocks. They do not only count down, they also count up. And every second that we are still here, still thinking, still reaching, still asking the question, is a second that the experiment has not failed. So maybe, just maybe, the silence of the stars is not a warning. Maybe it is an invitation, a vast empty stage, waiting for the first voice brave enough to sing. We do not know what happens next, but we know what the universe looks like right now. It looks like possibility. Enormous, terrifying, beautiful possibility. And if you have made it this far into this story, then you already know something important. You know that the question of whether we are alone is not really about the stars. It is about us. It is about whether we have the wisdom to match our curiosity, the patience to match our ambition, and the humility to recognize that being first is not a prize. It is a responsibility, the heaviest responsibility that any species has ever carried. Because if we get it right, the silence ends with us, and the cosmos will never be dark again. But if we get it wrong, the silence continues, and the next civilization to arise, 1 billion years from now on a rocky world orbiting a dim red star, will look up at the same quiet sky and ask the same question we asked. Where is everyone? And the universe will have no answer. If you found something in this story that changed the way you think about our place in the cosmos, consider subscribing and sharing it with someone who looks up at the stars the same way you do. Because these are not just questions for scientists. They are questions for all of us. And the more of us who are thinking about them, the better our chances of finding the right answers. But before we reach that conclusion, there is more to uncover. Because the story of our aloneness is not finished. There are layers to it that we have not yet explored. Depths to the silence that deserve to be heard. And the deeper you go, the stranger it gets. Let us return to the thermodynamic wall for a moment, because there is an aspect of it that we passed over too quickly. We talked about waste heat and Dyson swarms and the G-hat survey. We talked about the absence of infrared signatures in 100,000 galaxies. But we did not talk about what that absence implies about the fundamental nature of civilization itself. Here is the core of the argument. The second law of thermodynamics states that entropy, disorder, must always increase in a closed system. Every process that does useful work generates waste energy. This is inescapable. There is no technology, no matter how advanced, that can violate this law. It is as fundamental as gravity. For a civilization, this means that growth has a cost. Every additional unit of energy you consume generates waste heat that must be radiated away. And there is a limit to how efficiently you can radiate it. The larger you grow, the more waste heat you produce, and the harder it becomes to dispose of that heat without raising the temperature of your environment. Eventually, you reach a point where your own waste heat is cooking you. Your radiators cannot keep up. Your computational systems overheat. Your habitats become uninhabitable. This is the thermodynamic wall, and it applies to every conceivable technology. including technologies that we have not invented yet. It applies to Dyson spheres. It applies to Matryoshka brains, hypothetical computing structures that surround a star in nested layers. It applies to anything that converts energy into useful work. The implication is staggering. There is a maximum size for any civilization, determined not by ambition or resources, but by physics. A civilization that tries to grow beyond this limit will be destroyed by its own heat, and that maximum size is far smaller than the galaxy-spanning empires that science fiction imagines. This might explain the G-hat null result better than any sociological hypothesis. It is not that civilizations choose to stay small, it is that they have no choice. The universe enforces a speed limit on growth, and that speed limit means that even a civilization millions of years old might occupy only a tiny fraction of its galaxy, small enough to be lost in the noise, small enough to be invisible. Researchers have recently begun to formalize this idea. A 2025 paper explored what it called the mundane perspective on the Fermi Paradox. The paper argued that there is likely a practical ceiling on technological development, a maximum level of energy consumption and computational capacity beyond which further growth becomes impossible or prohibitively expensive. In this view, the most advanced civilizations in the galaxy might be significantly more capable than us, but they would not be the godlike entities that science fiction imagines. They would be limited, constrained, mundane. And a mundane civilization does not leave the kind of dramatic signatures that our surveys are designed to detect. It does not build Dyson spheres. It does not colonize entire galaxies. It does not broadcast powerful beacons. It lives within its thermodynamic budget, and from a distance, it looks like nothing at all. There is something almost Buddhist about this idea. The most advanced civilizations, the ones that have survived the longest, might be the ones that have mastered the art of wanting less, not because they lack ambition, but because they have learned that the universe rewards efficiency over expansion. This fits with another recent hypothesis that has been gaining attention in the astrobiology community. In a 2022 paper published in the Journal of the Royal Society Interface, researchers Michael Wong and Stuart Bartlett proposed what they called asymptotic burnout. The idea is simple and unsettling. Civilizations that grow without limit eventually hit a wall, not just of thermodynamics, but of complexity. Their systems become so interconnected and so fragile that a single failure can cascade through the entire structure. Like a city that has grown so large that a single power outage can shut down hospitals, water treatment, communication, and transportation simultaneously. Wong and Bartlett argued that civilizations face a binary choice. Either they learn to plateau, to stabilize their energy consumption and population and complexity at a sustainable level, or they burn out, crash, collapse, and the ones that plateau, the ones that achieve what the researchers called homeostatic awakening, become quiet. They stop expanding. They stop consuming more. They reach a steady state. And a steady state civilization is, from the outside, virtually invisible. Think about what this means for the Fermi Paradox. If the surviving civilizations are the quiet ones, the efficient ones, the ones that have mastered the art of living within their means, then the silence of the cosmos is exactly what we would expect. Not because nobody is there, but because the survivors have learned that growth is a trap, that the civilizations we are looking for, the loud ones, the expanding ones, the ones that build megastructures and colonize galaxies, are the ones that did not make it. The universe selects for quiet, and we are listening for noise. But this interpretation carries a warning for us, because right now, humanity is on an exponential growth trajectory. Our energy consumption is increasing. Our population is increasing, though it may soon plateau. Our computational demands are skyrocketing, driven by artificial intelligence and machine learning systems that consume vast amounts of electricity and generate enormous amounts of waste heat. Data centers already account for a significant and growing fraction of global energy use, and the trend is accelerating. If Wong and Bartlett are right, then we are currently on the burnout trajectory. We are the loud civilization, the expanding one, the one that is consuming more every year and radiating more waste heat into space. From the perspective of a hypothetical alien astronomer 1,000 light-years away, Earth's infrared signature has been getting brighter for the last 2 centuries. We are lighting up, and in the dark forest, lighting up is the most dangerous thing you can do. But we do not need the dark forest to see the danger. The danger is internal. It is the same danger that Wong and Bartlett describe. Growth without wisdom, expansion without sustainability, technology without temperance. The great filter, the dark forest, the thermodynamic wall, and asymptotic burnout are all pointing at the same conclusion from different angles. Civilization is fragile. Intelligence is rare. And the gap between what technology allows and what wisdom permits is the most dangerous territory any species will ever cross. We are in that territory right now, and we do not have a map. But there is something else that these hypotheses point toward, something that gets lost in the grimness of the analysis. And it is this: the fact that we are asking the question at all is remarkable. The fact that a species of upright primates on a small rocky planet has managed to look up at the sky and wonder about its place in the cosmos, that it has built telescopes and radio dishes and spacecraft and sent its gaze to the edges of the observable universe, that is not a failure. That is a miracle. Not a miracle in the supernatural sense. A miracle in the statistical sense. Given everything we know about the filters and the walls and the traps, the fact that we are here, right now, thinking these thoughts, is so improbable that it borders on the absurd. We are the universe becoming aware of itself, and whether that awareness is a flash in the dark or the beginning of a long, slow illumination depends entirely on what we choose to do with it. The Fermi Paradox is, at its heart, a mirror. It seems to be about the stars, about alien civilizations and radio signals and waste heat. But it is really about us, about our fears and our hopes and our deepest assumptions about the nature of existence. When we ask where the aliens are, we are really asking whether the universe is a place where intelligence can thrive, or a place where it inevitably perishes. And the honest answer is that we do not know. We know the obstacles, we know the filters, we know the walls. We know that the odds are stacked against any species that tries to bridge the gap between biological intelligence and lasting, sustainable interstellar civilization. We know that the silence of the sky is real and that it demands an explanation. But we also know something else. We know that the universe, for all its indifference, has produced at least one species capable of understanding its own predicament. One species that can look at the math and see the filters and still choose to keep going. One species that can contemplate its own extinction and decide consciously and deliberately that it would rather fight for survival than accept inevitability. That is not nothing. That might, in fact, be everything. Consider a thought experiment. Imagine you are a member of a civilization that arises 10 billion years from now, on a planet orbiting a quiet red dwarf star. Your civilization has access to the accumulated wisdom of billions of years of cosmic chemistry. Your planet is rich in phosphorus and molybdenum and all the trace elements that life requires. The conditions for your existence are, by every measure, superior to the conditions that produced us. But when you look back at the history of the cosmos, you find something astonishing. You find evidence of a species that arose during the very first epoch of cosmic habitability, on a planet that was only marginally suitable, around a star that was destined to burn out in a few billion years. A species that existed during the chemical adolescence of the universe, when the essential elements were scarce and the conditions were barely adequate. And yet, that species managed to survive. It figured out how to navigate the thermodynamic wall. It found a way through the biological filters. It resisted the temptation of endless growth and learned to live within its means. It crossed the gap between tribal instinct and interstellar wisdom, and it became the seed from which all subsequent life in the galaxy grew. Would you not be in awe of that species? Would you not consider their achievement to be the greatest in the history of the cosmos? That species could be us. It does not have to be. There is no guarantee. The filters are real, and the walls are real, and the dangers are real. But the possibility is real too, and the possibility is worth everything. Here is one more scientific puzzle to sit with as we approach the end of this story. In 2014, Avi Loeb published a paper about the habitable epoch of the early universe. He pointed out that when the cosmos was just 10 to 17 million years old, the cosmic microwave background radiation, the leftover glow of the Big Bang, had a temperature between 0 and 100 degrees Celsius. Room temperature, the temperature of liquid water. This means that if rocky planets existed at that incredibly early epoch, they could have had liquid water on their surfaces regardless of their distance from any star. The background radiation of the universe itself would have kept them warm. The entire cosmos was, briefly, a habitable zone. Of course, there is a problem. At that early stage, the universe had almost no heavy elements. The first stars were just beginning to form and had not yet lived long enough to die and scatter their ashes. Rocky planets, if they existed at all, would have been made almost entirely of hydrogen and helium, with barely a trace of carbon or oxygen or phosphorus. Life as we know it could not have formed, but the idea is haunting. A universe that was warm enough for life before it had the chemistry for it. A cosmos that was ready in one way and utterly unready in another. Like a house that has been heated and furnished, but has no food in the kitchen. And now, 13 billion years later, the kitchen is finally being stocked. The heavy elements are accumulating. The phosphorus is building up. The conditions are reaching the threshold where complex biochemistry can begin. And we are here right at the threshold watching the supplies arrive. We are early. We are improbable. And we are, perhaps, the most important thing the universe has ever produced. Not because we are special in any inherent way. Not because there is something magical about human DNA or human consciousness, but because we are here first. And being first means that whatever we do next echoes forward through time in ways that nothing else can. If we survive, we become the template. The first data point in the long experiment of cosmic intelligence. The species that proved it could be done. If we do not survive, we become a ghost. A brief flicker in the fossil record of a planet that will one day be swallowed by its own star. A cautionary note in the chemistry of the cosmos, read by no one, mourned by nothing. The Fermi Paradox asks where everyone is. And after walking through the evidence, after examining the filters and the forests and the walls and the timing, the most honest answer we can give is this: they are not here yet. They are waiting in the future, on worlds that are still forming around stars that are still young. They will arrive eventually in their own time, when the chemistry is right and the conditions are met. And when they do, they will look back at the early universe and wonder about the species that came before them. What they find, what story we leave behind, is up to us. The night sky is not empty. It is patient. It is waiting for a universe that is still growing into itself, still accumulating the ingredients for the greatest experiment in existence. The experiment of life, of intelligence, of civilizations that learn to last. And we, impossibly, improbably, beautifully, are the ones who get to go first. That is not a tragedy. That is the most extraordinary privilege in the history of the cosmos, but only if we treat it as one. The stars are quiet tonight. They will be quiet tomorrow, and they will be quiet for a very long time. But the silence is not a threat. It is not a warning. It is a gift, a blank page, an open road, a universe that is holding space for something that has never existed before. Us, and whatever we choose to become. So the next time you look up at the night sky and feel that ancient instinctive chill, that sense of being small and alone in something too vast to comprehend, remember this: you are not alone in the way you think. The universe is full of potential, waiting to be realized. And you are part of the first generation of minds to recognize that potential for what it is. The Fermi Paradox has been solved, not with a single clean answer, but with a tapestry of answers, each one woven from different threads of evidence: the biological filters, the chemical timing, the thermodynamic constraints, the dark forest dynamics, the asymptotic burnout. Each one contributes a piece to the picture. And when you step back and look at the whole thing, the picture that emerges is not one of despair. It is one of possibility. We are early. The universe is still young. The best is yet to come. And we are the first eyes to see it. That is the answer to the Fermi Paradox. And it should not exist like this. Because the answer tells us that the silence is not a mystery to be solved. It is a moment to be lived. The quiet before the dawn. The stillness before the first note of a symphony that will play for trillions of years. And we are the ones who get to write the opening bars. Close your eyes. Breathe. Let the silence settle around you like a blanket. And know that out there, in the dark, the universe is not empty. It is waiting. And it has been waiting for a very, very long time. For us. But we said the silence should not exist like this, and we have not fully explored what like this means. So let us go deeper. Let us look at the silence from angles we have not yet considered, because the more carefully you examine it, the more it reveals. There is a concept in astronomy called the cosmic microwave background, the oldest light in the universe. It is the afterglow of the Big Bang. A faint radiation that fills every corner of the cosmos, stretched by the expansion of space into microwave frequencies. It was released roughly 380,000 years after the Big Bang, when the universe cooled enough for the first atoms to form and for light to travel freely through space for the first time. This background radiation is remarkably uniform. In every direction you look, it is almost exactly the same temperature, about 2.7 Kelvin, just a few degrees above absolute zero. The uniformity is itself a puzzle, because it means that regions of the universe that should never have been in contact with each other somehow reach the same temperature. The leading explanation, cosmic inflation, proposes that the universe underwent a brief period of exponential expansion in its first fraction of a second, stretching a tiny, uniform patch of space into the entirety of our observable cosmos. But here is the part that matters for our story. That background radiation is cold now, But it was not always cold, and its temperature at any point in history is precisely known. When the universe was about 15 million years old, the cosmic microwave background had a temperature of roughly 27 degrees Celsius, room temperature, the temperature of a comfortable spring afternoon. If rocky planets had existed at that time, which is theoretically possible though unlikely, they would have been bathed in warmth from every direction. They would not have needed a star to keep them warm. The universe itself was the heater. Liquid water could have existed on any rocky surface, anywhere, regardless of its distance from any light source. This is what Loeb called the habitable epoch of the early universe, and it lasted for a few million years, a window during which the entire cosmos was, in principle, habitable. But the chemistry was not there. The first stars had barely begun to form. The heavy elements needed for rocky planets and organic molecules did not yet exist in meaningful quantities. The universe was warm enough for life but had nothing to build life from. A house with a thermostat set perfectly, but no furniture, no food, no tools. It is a remarkable coincidence, or perhaps not a coincidence at all, that the conditions for life, warmth and chemistry did not overlap until much later. The warmth came first, billions of years before the chemistry was ready. Then the warmth faded as the universe expanded, and the chemistry slowly accumulated as generations of stars lived and died. By the time the chemical conditions were right, the cosmic warmth was gone, and life needed stars to provide localized heating. We exist in the era where these two curves finally crossed, where enough heavy elements had accumulated for complex biochemistry, and where stable, long-lived stars could provide the consistent warmth that the cosmic background no longer supplied. This crossing point, this narrow window where chemistry and energy align, is where we find ourselves. And the window only opened recently, in cosmic terms. The Earth formed 4.5 billion years ago, roughly 9 billion years after the Big Bang. But most astrobiologists agree that the heavy element enrichment of the galaxy reached a level sufficient for complex, phosphorus-dependent biochemistry only about 5 to 6 billion years ago. That gives us a window of perhaps 5 to 6 billion years, during which planets like Earth could have formed and developed life. 5 to 6 billion years. That sounds like a lot. But compare it to the total lifespan of the smallest red dwarf stars, which will burn for 10 trillion years. Our window is a tiny sliver at the beginning of a vastly longer era. We are not just early. We are absurdly early. Now consider another puzzle. If the conditions for life have only recently been met, then there should be very few civilizations in the galaxy right now. But very few is not the same as zero. If the chemistry has been adequate for 5 or 6 billion years, and if life can arise on planets that are even slightly older than Earth, then there might be a handful of civilizations in the Milky Way that are a few billion years more advanced than us. A few billion years. Try to imagine what that means. A civilization that has had a billion years more time than we have had to develop technology. We went from stone tools to spacecraft in roughly 2 million years. What does another billion years of development look like? We cannot even conceptualize it. It is like asking a bacterium to imagine a city, and yet, if such civilizations exist, they are invisible to us. They are not broadcasting. They are not building visible megastructures. They are not colonizing the galaxy in ways that our telescopes can detect. Either they do not exist, which is consistent with the cosmic timing argument, or they exist and are fundamentally undetectable, which is consistent with the thermodynamic wall and the homeostatic awakening. There is a third possibility that we should consider, even though it is the most speculative of all, and it is this: what if advanced civilizations are not just quiet? What if they are incomprehensible? This is sometimes called the Transcension hypothesis, proposed by futurist John Smart. The idea is that sufficiently advanced civilizations do not expand outward into space. Instead, they expand inward into ever denser, more efficient computational substrates. They compress themselves. They move toward the smallest possible physical scales, where the most computation can be done per unit of energy. They dive into the realm of nanotechnology, femtotechnology, even Planck-scale engineering, reaching for the fundamental limits of what physics allows. In this scenario, an advanced civilization does not look like a sprawling galactic empire. It looks like a small, ultra-dense object that is almost impossible to distinguish from a natural phenomenon. It might look like a particularly odd neutron star, or a black hole with unusual properties, or a region of space with anomalous gravitational signatures. It would be there, but we would not recognize it for what it is. This is, admittedly, highly speculative, but it is consistent with the thermodynamic arguments we have discussed. A civilization that compresses itself maximizes its computational efficiency and minimizes its waste heat. It becomes the smallest possible target in the dark forest, and it achieves the homeostatic stability that Wong and Bartlett described. Whether or not the Transcension hypothesis is correct, it highlights an important limitation of our search. We are looking for civilizations that look like us, or like what we imagine we will become in a few centuries. We are looking for radio signals and infrared waste heat and atmospheric pollution and megastructures. But if the most advanced civilizations are nothing like us, if they have evolved beyond anything we can currently imagine, then our search strategy might be fundamentally flawed. We might be looking for the wrong thing. Imagine a fish in the deep ocean, a creature that has never seen sunlight, that navigates by bioluminescence and pressure waves. Imagine that fish trying to detect a satellite orbiting above the ocean surface. The fish has no concept of electromagnetism. It has no way to detect radio waves. The satellite might as well not exist, not because the satellite is hiding, but because the fish's entire sensory and conceptual framework is incapable of perceiving it. We might be that fish. This is a humbling thought, but it is also liberating, because it means that the silence of the cosmos might not be saying what we think it is saying. It might not be saying nobody is there. It might be saying you do not yet have the eyes to see. And if that is true, then the story of the Fermi Paradox is not a story of absence. It is a story of immaturity. We are a young species with young technology, looking at the cosmos through instruments that can detect only the crudest signatures of intelligence. As our technology matures, as our understanding deepens, the silence might gradually fill with signals that were there all along, hidden in frequencies and formats and phenomena that we had not thought to look for. The next generation of telescopes might change everything. The James Webb Space Telescope is already detecting atmospheric compositions of exoplanets in ways that would have been impossible a decade ago. The upcoming Habitable Worlds Observatory, if funded and built, will be specifically designed to search for biosignatures in the atmospheres of Earth-like planets around nearby stars. The Square Kilometre Array, a radio telescope currently being built across South Africa and Australia, will have the sensitivity to detect the equivalent of airport radar from nearby star systems. Each new instrument expands our ability to see, and each expansion of vision carries the possibility, however remote, that we will finally hear something in the silence. But until that day comes, we sit with the quiet. And the quiet asks us to think carefully about what it means. It might mean we are alone. It might mean we are early. It might mean we are blind. It might mean we are surrounded by civilizations that have learned the same lesson, that survival in the cosmos requires stillness and patience and the wisdom to stop reaching for more than you need. Each of these possibilities tells a different story about the universe, but all of them tell the same story about us. We are a species at the very beginning of its journey, a species that has just barely crossed the threshold from ignorance to awareness, a species that has discovered, in the span of a single human lifetime, that the cosmos is both far vaster and far quieter than anyone imagined. And now we have a choice. We can look at the silence and despair. We can see the filters and the walls and the traps and conclude that the universe is hostile, that intelligence is doomed, that our brief flicker of awareness is destined to be snuffed out like every other candle that has been lit in the dark. Or we can look at the silence and see something else entirely. We can see opportunity. We can see an empty stage, waiting for the first performance. We can see a blank canvas, waiting for the first brushstroke. We can see a future so vast and so open that it takes your breath away. The Fermi Paradox tells us that the cosmos is quiet, but it does not tell us why. And in that uncertainty, in that gap between the question and the answer, there is room for something that the equations cannot capture, something that the telescopes cannot detect, something that is perhaps the rarest and most precious thing in the universe. Hope. Not blind hope, not naive hope, but the kind of hope that comes from looking honestly at the evidence, acknowledging the dangers, and choosing to keep going anyway. The kind of hope that builds telescopes and sends probes to distant moons and studies the chemical compositions of stars 1,000 light years away. The kind of hope that refuses to accept the silence as final, because the silence might not be final. It might just be temporary, and we might be the ones who break it. The stars are quiet tonight. They have been quiet for as long as anyone has listened. But somewhere out there, on a planet we have not yet discovered, orbiting a star we have not yet named, the chemistry might be coming together right now. The first molecules might be linking up. The first membranes might be forming. The first flicker of what will eventually become awareness might be stirring in a warm, dark ocean under an alien sky. They do not know about us yet. They will not know about us for a very long time. But when they do, when they finally develop the technology to look back across the gulf of time and space that separates them from us, they will find something remarkable. They will find that they were not the first. And they will know, because we will have left evidence, that it is possible, that a species can arise from the chaos of chemistry and evolution, can survive its own technology, can learn to live within the limits the universe imposes, and can endure. That is the legacy we could leave, not a signal in the radio spectrum, not a megastructure around a star, but proof, simple, undeniable proof that it can be done, that intelligence can survive, that the great filter can be passed, that the dark forest can be navigated, that the thermodynamic wall can be respected without being defeated by it. That would be worth more than all the gold in all the asteroids, in all the galaxies, in the observable universe. And it starts here, tonight, with a question, asked over lunch at Los Alamos in 1950, and carried forward by every human who has ever looked up at the stars and felt the weight of the silence pressing down. Where is everyone? Maybe they are waiting for us to show them the way. There is one more thing, one more puzzle that we have not yet discussed, and it might be the strangest of them all. In 2022, the James Webb Space Telescope began its science operations, turning its golden mirror towards some of the most distant objects ever observed. within months, it started sending back results that surprised astronomers. Galaxies that were far more massive, far more structured, and far more luminous than existing models predicted for the early universe. Galaxies that appeared to have formed impossibly fast, assembling billions of stars within a few 100 million years of the Big Bang. These early galaxies are a puzzle because our models of galaxy formation say they should not exist, at least not at the sizes and luminosities observed. Something in our understanding of how structure forms in the universe is incomplete. Either the early universe produced stars more efficiently than we thought, or there are physical processes at work that our models do not capture. Now, this is a cosmological puzzle, not a Fermi Paradox puzzle, but it connects in an important way. Because if our models of the early universe are incomplete, then our models of chemical enrichment are also incomplete. The rate at which heavy elements accumulated in the cosmos, the timeline of when the essential ingredients for life became available, these depend on assumptions about star formation and stellar death that the Webb observations are now calling into question. It is possible that the chemical conditions for life were met earlier than we think, or later, or in a more uneven distribution across the galaxy than our models predict. Every revision to our understanding of cosmic chemistry is also a revision to our understanding of when and where life could have begun. This is the frontier, the place where the Fermi Paradox meets cutting-edge astrophysics, and it is changing fast. There is also the mystery of fast radio bursts to sit with a little longer. We mentioned them briefly in the context of the dark forest, but they deserve a deeper look. First detected in 2007 by astronomer Duncan Lorimer in archival data from the Parkes Radio Telescope in Australia, fast radio bursts are millisecond-long flashes of radio energy that arrive from billions of light-years away. Despite their brevity, they carry enormous energy. A single burst can release as much energy in a millisecond as our Sun produces in decades. As of the mid-2020s, hundreds of fast radio bursts have been catalogued. Some repeat from the same source. Most are one-time events. The leading explanation is that they are produced by magnetars, highly magnetized neutron stars that undergo violent flares. This was supported by the detection of a fast radio burst from a known magnetar in our own galaxy in 2020, confirming that at least some bursts have this origin. But not all of them fit the magnetar model cleanly. Some repeating sources show complex patterns that are difficult to explain with a single magnetar. Some bursts have properties like extreme polarization or unusual spectral structures that push the boundaries of what magnetar models predict. The field is still young, and new discoveries are arriving faster than theories can accommodate them. This is the nature of frontier science. Every answer generates new questions. Every explanation reveals new mysteries. And every mystery carries, however faintly, the possibility that we are seeing something we do not yet have the conceptual tools to understand. The same can be said for another class of unexplained signals. In recent years, the Breakthrough Listen project has sifted through petabytes of data from the Green Bank Telescope and the Parkes Telescope, searching for narrow-band signals that might indicate artificial transmitters. In 2020, they detected a signal from the direction of Proxima Centauri, the nearest star to our Sun. The signal, designated BLC1, was narrowband, appeared to come from a specific point in the sky, and drifted in frequency in a way consistent with a signal from a source not on Earth. For a few breathless weeks, BLC1 was the most exciting signal in CT history since the WOW signal. But careful analysis eventually revealed that it was almost certainly a form of human-generated radio interference, probably from electronic equipment near the telescope that happened to mimic the characteristics of an extraterrestrial signal. The episode was both disappointing and instructive. It showed how easy it is for false positives to arise. It showed how rigorous the SETI community is in vetting its own results, demanding extraordinary evidence before making extraordinary claims. And it showed, perhaps most poignantly, how desperately we want to find something, how much the silence weighs on us, how ready we are to hear a voice in the static. We have not heard that voice, not yet, but we have not stopped listening. And the search is becoming more sophisticated every year. Machine learning algorithms are now being deployed to analyze radio data in real time, flagging anomalies as they occur rather than after the fact. New telescope arrays are coming online with unprecedented sensitivity and sky coverage. The tools are getting better, and the haystack is being searched more thoroughly than ever before. If there is a needle in it, we are more likely to find it now than at any point in human history. But if there is no needle, if the silence is real and permanent, then that too is an answer. An answer that carries its own strange and terrible beauty. Because a silent universe is a universe that is waiting. And a universe that is waiting is a universe that is full of potential. Cool. Every quiet star is a possible home. Every lifeless planet is a possible garden. Every empty light year is a possible road. The silence is not a wall, it is a door. And we are standing on the threshold, looking out at the most extraordinary landscape that any eyes have ever seen. A landscape that stretches not just across space, but across time. Across billions of years of past and trillions of years of future. Across every possible configuration of matter and energy and chemistry and life that the universe can produce. And we are here, right at the beginning, holding the first candle. The Fermi Paradox asks the most important question science has ever posed. Where is everyone? And the answer, built from decades of observation and theory and careful, painstaking analysis, is that the question itself is premature. We are asking where is everyone at the very start of the game, before the other players have had time to arrive. We are the early birds, sitting in an empty theatre, wondering why the show has not started yet. The show has not started because the universe is still setting up. The lights are still being hung. The instruments are still being tuned. The chemistry is still being mixed. And we, impossibly and beautifully and terrifyingly, are part of the setup crew. That is the Fermi Paradox, solved. Not with a single answer, but with a constellation of answers, each illuminating a different facet of the same extraordinary truth. We are early, we are rare, we are fragile, and we are, for the moment, alone. But alone does not mean abandoned. Alone means first. And first means that everything that comes after us, every civilization, every mind, every moment of cosmic awareness, will owe something to whether we succeed or fail. That is the weight of being first. And that is the privilege. The stars will still be there tomorrow, and the day after that, and for billions of years after that. They are patient, and they are waiting. And somewhere, on a world that does not yet exist, orbiting a star that has not yet been born, something wonderful is going to happen. Because of us, or in spite of us, but because we were here. The silence is not the end of the story. It is the beginning. And beginnings, by their nature, are full of possibility. Rest now, the stars will keep. And when you wake up, they will still be there, quiet, patient, waiting, just like us.